Good morning, everyone. I hope that you guys had a great weekend. Today is the 18th of November, and so we have an exam on Thursday. Now, I'm going to send out some announcements regarding the exam. This exam is scheduled for Thursday and Thursday alone, but in an effort to give you guys a little bit more flexibility, I think what I'm going to do is I'm going to have the exam open at 8 a.m. and close at 8 p.m. Now, I want to give you guys the caution and the notice that if you elect to take the exam at, say, 8 p.m., or no, not 8 p.m., sorry, if you elect to take the exam or start the exam at 7 p.m. and you encounter some sort of technical problems, the chances are pretty slim that I'll be able to help you. And the chances are pretty slim that I'll be responsive to any sort of email at that time. So my advice is to get the exam done as soon as possible. Now, like I said, like I said, it will be 8 to 8. It will close promptly at 8 p.m. Um, now, in terms of content on this exam is going to have a little bit of stuff from exam two. There won't be any explicit questions from exam one or that content. It will be exam two and exam three content. Now, to reflect back and go through, well, what's on this exam? What should I anticipate? We'll click here. This is on our home page. We'll go back to October. And if you scroll down, well, what stuff is going to be on this exam is going to be started on the 28th of October, which is a discussion of solutions. So to what I'm going to do is just kind of go through each one of these different blocks. And if you have any questions, please go ahead and email me. Or not email me, I'm sorry, just add it to the chat. So solutions, that is going to be a part of our exam and doing calculations related to solutions. Now, knowing terminology like solvent or solute is going to be very helpful for you. So a solute, it's a purple. Let's try something a little bit more apparent. Clear all drawings. And then, yeah, there we go. The solute. Well, that's the thing that's in lower abundance in a solution. The solvent is the thing that is in greater abundance. So you could think about it in terms of those, just simply amounts. So another way you could think about it is, well, what actually dissolves? The solvent is what is going to dissolve. The solvent is what causes something. Oh, that's what it is. Causes something to dissolve. So thinking about like that, I think would be a helpful way to, or that's another helpful way to think about solutions. Now, typically, or a question that you might see would be something like, okay, in a solution of salt water, what is the solute and what is the solvent? Well, the solute is going to be salt, and the solvent is going to be water. Okay. Now, water is kind of the it's commonly known as the universal solvent because it causes lots of things to dissolve. Now, that is that. Okay, I'm gonna clear all my drawings here. Now we'll go down. Soluble versus insoluble. If something is soluble, it goes into solution. If something is insoluble, it does not. So I use the example of whey protein. A good high quality whey protein goes into solution and therefore is soluble. A lower quality or kind of the wrong um, protein to drink as kind of a supplement to your diet would be an insoluble one because you're going to end up kind of chewing that. I always think of extreme examples, so let's go with sugar is soluble. Steak. Yes, I do mean a steak that you'd get from the butcher at HEB or, well, just the meat area at HEB. A steak is going to be insoluble. Okay. When it comes to solubility, a polar substance will dissolve very well in a polar solvent. So a polar solute goes into a polar solvent very well. Um, a non-polar solvent, so polar solute, or sorry, let me change that. Solvent will dissolve polar solutes, ionic solutes very well. A non-polar, I'm just going to write it, vent. Could you give me a one in the chat if you understand what I mean by vent? And I'm not talking about an air vent. I was saving myself like 3 seconds of writing. Not even that. Non-polar solvent is really good for dissolving a non-polar solute. A polar solute and a pol or an ionic solute is not going to go into a non-polar solvent well. So like dissolves like. Next up is quantitation. Could anyone give me in the chat what is the letter that we use for the unit of concentration? Or if you don't know the letter, what is the unit? Capital M. Good job, Kelly. So capital M stands for molarity. That capital M molarity is moles per liter. Now, that basically gives you a ratio. So when we talk about molarity calculations, there's a couple of different ways that you could do it. But before we get to that, this is showing a concentrated solution right here and a less concentrated or a more dilute solution on the far right. Now, you can quantify these. What I want you guys to be able to do is if I give you information about, let's say, 12.2 moles of NaCl dissolved in 346 liters of solution. Could you do that calculation? Well, that calculation's pretty easy as long as you know this formula right here, and that is going to be 12.2 divided by 346. So I'm going to pull this up on my calculator just so I can do this. I hope that somebody else is doing this alongside me so that they can see that number as well. 12.2 divided by 346 is 0.035. I'm sorry, Nick, that's my poor handwriting. That's a 12.2. So 12.2 divided by 346 gives us a concentration of 0.035 molar. Um, so this is a good calculation to be able to do. Similarly, a good calculation that you should be able to do would be something like 17.2 moles of NaCl dissolved in, let's go with 12,000 milliliters. Well, how would we do that? We'd have to take this unit, 12,000 milliliters, and convert it to liters. And this particular unit right here, milliliters, and this conversion, milliliters to liters, is a good one for you to know because I use it quite often. So 1,000 milliliters is equal to 1 liter. Therefore, 12,000 milliliters is equal to 12 liters. So we'd say 17.2 divided by 12 liters, or 17.2 divided by 12, which gives us 1.43 molar. Okay, so being able to do this sort of calculation is valuable. Understanding also how to take, 7 grams of solute in 125 milliliters. Okay. How would we do this sort of calculation? Well, first of all, we'd have to know what is the identity of that solute. And let's say for the sake of memory, let's say that it is NH3. And NH3 is going to be, I think that's 18 grams per mole. Let me do this, look this up real quick. Um, and of course, you have a periodic table, or you'll have a periodic table on your exam. So all that you would have to do is say 7 grams of NH3, and then compare that to the molar mass of NH3 of 17. 17.0 grams of NH3. Could anyone add to the chat, what am I solving for whenever I do 7 grams of, the information from the table versus this? Can somebody add to the chat what I'm solving for here? Okay, so what I'm solving for here is exactly, I'm solving for the number of moles of NH3. This is my kind of hypothetical question. 7 grams of NH3. Okay, that's my solute. And this is dissolved in 125 milliliters of a solution. So since I'm given the grams of NH3, I need to convert it to the moles of NH3. Could everyone give me a 7 in the chat if they follow that first part of the question? Okay. So that's what this calculation is for. This is 7 divided by the molar mass of NH3. So the 7 grams that I was provided with, or that I was told in the question, 7 divided by 17, which is the molar mass of NH3, that gives me 0.417 moles NH3. Give me a Y or an N. Am I done with this question? If I'm trying to find out the molarity of this, I'm not quite yet, but I'm close. So I'm done with this part of it. So essentially this number can be plugged in right there. So I'm going to clean this up just a little bit, and I'm going to say, all right, well, 0.417 moles of NH3. And I'm going to put in parentheses solute. And I'm going to divide this by 125 milliliters. That is the volume of my solution. Could anyone tell me if I need to change this number, or should I just do 125? Do I need to change it Y or N? Or do I need to do anything to it? Yes, I do. Because remember, my units are milliliters, and I need to convert this to, Kelly, spot on. Absolutely, great job. I need to convert it to liters. Well, if I have 125 milliliters, 125 ml is equal to 0.125 L. Okay, could everyone give me a star in the chat if you're good with this, where we've come to right now? Okay. Now, I'm going to go ahead and plug this in. 0.417 divided by 0.125, and I get a solution with a concentration of 3.336 molar. Okay, could everyone give me an 8 in the chat if, hey, I followed that. I think I could do that. And any other character, if you're like, there was a point where I lost you. Okay. So when you're looking at this slide right here, I want you to think about this almost like, well, what are the questions that you should be able to answer? I'm going to put a circle and a 1 inside that circle for this right here. If I give you the number of moles and I give you the volume in liters, think about that as like your entry level question. That's the basis question, or that's the basic question. Then down here at the bottom, I'm going to put a 2 right here. Well, is this question a little bit more challenging? It is, because the unit that's in the denominator, we need to do something with it. So that's like, you don't just get to take the numbers and plug them in and you're done. Instead, one of those two numbers, you have to modify it. You have to put it, you have to check the units and make sure that the units are correct. Okay, so this would be my second level question. Over here, where I'm going to put a 3 in a circle, this question where we took the mass and then we convert it to the number of moles. Okay, so mass to mole conversion. That's a conversion. So we had to change something about the number that goes on the top, the amount of the solute. And then we had to do the same thing with the number that's in the denominator. So we originally started with 7 over or 7 and 125, and we ended up with 0.417 and 0.125. So this sort of question would be like your third level type of question. Arguably, this would be the hardest of these sorts of questions. Now, I want you to expect and to anticipate you're going to see one of each of these. Now, why would I give you one of each of these? Well, like I said, this is kind of your basic question. If you don't know how to answer this, it's unlikely you're gonna get this, and it's unlikely you're gonna get this. But this is a way of evaluating, like, where is the gap in my knowledge? If you know how to do this, awesome. Easy peasy. All that you have to do that sort of question is know this, moles per solute. The next level is, okay, now I have to think about milliliters to liters. Oh, how do I count moles in C6H12O6? Okay, so yes, you do. So Kelly sent this question. Um, does the question have a mass associated with it? So actually, if I wanted the molar mass of C6H12O6, what I would do is I would say, okay, what's the mass of carbon? Carbon is 12. That's where the C12 comes from. I can multiply that by 6. So that's going to give me 72. Then I'm going to bring down hydrogen. And that's going to be 12 times H, which H has a mass of 1. So that's going to be plus 12. And then oxygen, I just remember this. So 6 times oxygen, which is 16. So 6 times 16 is going to be 96. 96. So 72 plus 12 is 84 plus 96 is 180 grams. So the molar mass of this is 180 grams. Now, I got a private message question. The question reads, I know it's unrelated, but could you do the polarity calculation for C6H12O6? I think that's what I struggled with on last test. Okay, so polarity in terms of if you were looking at this and you were asking, or sorry, before I move on, Kelly, you had that question about C6H12O6. Did that answer your question or was there more to it? Okay, great. So C6H12O6. Now, I will draw C6H12O6 right now, but actually, you know what? C6. Sorry, I'm just repeating myself because I'm trying to think out what is the most important information that I want to share. So the question is the polarity calculation. Are you asking about electronegativity? Because calculating electronegativity about an entire molecule is going to be a little bit difficult because you have lots of different bonds. Now, with that in mind, though, I'll draw here. This is an example of a Lewis structure of C6. Actually, you know what I'm going to do? And I'm sorry for repeating myself, but if anyone wants a screenshot or the information that's on the screen right now, go ahead and take that screenshot because I'm going to clear the drawings in 5, 4, 3, 2, 1, clear. Okay. So if I'm looking at C6, H12, and I don't expect you guys to know what C6H12O6 looks like. Um, I think the last test had a lot of is this polar or non-polar and had longer molecules like that. Okay, so if this question is just, I'm going to start over. I'm just going to erase that. Um, I'll give you two different molecules, C6H6 versus C6H12O6. This molecule right here is nothing but carbons and hydrogens. This is a non-polar molecule. It's a non-polar molecule because the carbons and hydrogens, they have no electronegativity differences, or virtually no electronegativity differences. Now, as soon as you introduce something like oxygen, well, chances are that when you introduce oxygen, you're going to introduce something like this. I'll just go with this group right here. So I'll just draw, this is a simplified molecule, but it achieves sort of the same thing. Um, this group right here, this oxygen hydrogen, that's commonly known as a hydroxyl bond or hydroxyl group. Now, that's a term that I've mentioned maybe, but it hasn't been a priority. What has been a priority, though, with respect to a molecule like this is, could anyone tell me what type of interaction this group would love to participate in? And I'll narrow your scope a little bit. It's not a covalent bond because that's an intramolecular interaction. But what type of intermolecular interaction will this group love to participate in? Hydrogen bonds. Anything, if essentially, if you see lots of hydrogens and oxygens, I want you to think, aha, that's going to love hydrogen bonding. Okay. And if something loves hydrogen bonding or can participate in hydrogen bonding, that is a polar group. Group. And that makes this whole molecule a polar molecule. Does that address your question, or do you have more questions about the person who sent me the private message? And if you have more questions, that's absolutely fine. Okay, I'm happy to see that. All right. Absolutely. Thank you for asking. Okay, so could you give me a 1 to 5, one being I feel really good about this, a five being I don't know about this, with respect to those three levels of molarity calculations? One being I'm good, three being or five being uh-oh, three being three being I think I'll be good by Thursday. I got another comment about polarity. And all right, I got a question or a comment that read, that's what I had trouble with on the last test as well. Okay, let me give you kind of a general idea because I feel like the two people who messaged me are not the only people. Let's see, do I have, okay. What I'm gonna do is just I know. I just want to give myself like a blank space to write on where there's no sort of distractions, I guess. And yeah, I guess this is it. Sorry. Um, and I'm happy that you're asking about this because this relates to polarity, or this polarity discussion is important for our discussions of, well, will something dissolve or not? So polar and non-polar. Now, if a substance is polar, there's a couple of things that you should look for. OH. If you see an OH on a molecule, chances are that molecule's polar. For a non-polar compound, what you should look for are lots of carbons and hydrogens. And I would go ahead and put a little asterisk by this and say exclusively. Okay. Now, in addition to OH, if you see NH or FH, these are all good signs that you are talking about a polar molecule. Okay. Now, with that in mind, I'm happy to see the response on the molarity. It looks like folks, maybe a couple more practice problems or, just kind of make up a practice problem for yourself, and that will put you in a good place. So, polar compounds. Tell me, is H2O polar or non-polar? P for polar, N for non-polar. Polar. You're absolutely right. Okay, so now will CH4, don't answer if it's polar or non-polar, but instead tell me, will this CH4 dissolve as a solute in H2O as the solvent? Will that dissolve in there well? Give me a 1 for yes, it will, and a 5 for no, it won't. Great. 5, it won't. Okay. The reason for that is H2O is polar. CH4 is non-polar. Now, I'm going to double down on this. What about C2H6? Will that dissolve in water well? Give me a 5 for no, it won't, or a 1 for yes, it will. Spot on. It will not. C2H6 is not going to dissolve well in H2O. Now I want to flip something on you. Okay. Let's say that I had C5H10. C5H10. This is a compound known as pentane. Okay. Will C2H6, let's say that this was a liquid, would C2H6 dissolve or go into this solution well? Y or N? Yes, it will, or no, 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 it won't. You're right, it will. It absolutely will. Why is that? Well, C5H10 is nonpolar. NP. C2H6, nonpolar. So a nonpolar substance goes into a nonpolar substance or mixes really well with a nonpolar substance very well. So I think that if you, and then other things related to, so these are the first few things to look for to classify something as polar or nonpolar. Other things to look for are ideas like the molecule is not symmetrical. So there's no symmetry. Does anyone remember, is a symmetrical molecule, if a molecule has symmetry, that means it's the same on both sides. Is that going to be P polar or N nonpolar? If it's symmetrical, if there's symmetry. You're right. If a molecule has symmetry, chances are greatest that it is nonpolar. So if something has symmetry, it is nonpolar. If something does not have symmetry, then it is polar. Okay, so these I think would be really helpful kind of ideas and guidelines that, would go really well on that little index card. All right, I'm going to clear my drawings because we want to wrap this up. And I'm going to zoom back out. I'm going to scroll, 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 because now what I'd like to talk about is dilutions. Solution dilution. I always kind of think about this as like, um, I like to think about examples like Kool-Aid or something. But this is also something that you could relate to like, well, here. Um, could you give me a 7 in the chat if you like sweet tea? And if you don't like sweet tea, that's fine as well. But just indulge me that unsweet for life. Word. Smart. Good. So let's say that you get a sweet tea. And your friend, yeah, you get a sweet tea, and your recipe is, yeah, sure, there's some tea in there, but most importantly, you've got a ratio. You've got 1 gallon of sweet tea, and that gallon of sweet tea requires, let's go with 2.5 pounds of sugar. That seems about right. I don't know. That's a lot of sugar for not a lot of amount. Now, let me ask you this, and this is just to kind of highlight this solution preparation. Um, if you were to make this sweet tea, we've got two options. Option one and option two. Option one is you get the 1 gallon jug and you fill it up with water to 1 gallon. And then you add, so first, second, you're going to get sugar. And third, you're going to get the tea. So you fill the jug up to 1 gallon, that water level. Then second, you're going to add sugar. And then third, you're going to add the tea itself. My screen is still zoomed in. Uh-oh. That seems, let's see, where are we? Where are we? My screen is still zoomed in. You know what? I'm going to stop my share and I'm going to restart it. How's it look now? You guys can see the solution dilution slide, correct? Give me a Y or an N to the chat. Okay. Okay, good. Um, okay, so you're making tea. You've got annotate. Annotate, come on. There we are. We got two options, 1 and 2. The first option is you get a recipe is 1 gallon. This is how to make 1 gallon of sweet tea. You get water, 2.5 pounds, sugar, and tea bags. 5, yeah. Okay. Okay. So we've got two options. One is you get a gallon of water. Add that to the bucket, then add sugar, and then add tea, and then you put it outside and you kind of bake out there for a little while. This is one option where you get that gallon of water. The second one is you get sugar. So you get the sugar first, then you add the tea, and then you add the water. And of course, you stir to make sure it dissolves. Could somebody tell me, 1 or 2, which is the sequence that you're going to do it in? if your goal is to make 1 gallon of tea. Is it the first or the second one? Kelly, you're absolutely right. We got to do the second one. Why is that? Well, because if we did number one, here's our bucket. We got water. If we added sugar to this, what's going to happen to the water level? It's going to go up. Are we going to make more than 1 gallon with this? Yes, we are. Is it going to taste the exact same as this other one? No, it's not. Because this one right here, option two, has more sugar or it has a higher sugar to water ratio. And this is the ideal. This is the correct way of doing it. Okay, so could you give me a three in the chat if you follow that? And give me any other character in the chat if that doesn't make sense to me. Okay. So I'm going to clear all my drawings, and I made my sweet tea. And I've got 1 gallon of it. And let's say that, this is like the perfect level of sweetness for you. Um, but somebody comes up to you and they say, you know what, that's too strong for me. I don't like it. It's way too much. I need about half as much sugar. This formula right here gives you a way to calculate how to make that for them. And listen, this is your friend, so you're not going to be like, well, sorry. You're going to say, okay, you know what? I can help you out with that. So in this case, what I'm going to do is I'm going to say that let's say that the concentration of our sweet tea was 3 molar. I'm just putting a random number out there. Okay, so let's say that it's 3 molar. Could somebody tell me what is the concentration of the desired sweet tea for your friend? If they want it half as strong, what is their concentration of sweet tea that they want? 1.5. Perfect. So they want their sweet to be 1.5 molar. And you're like, okay, cool, I can do that. Now, let's say that this person says, I want 1.5 molar and I'm super thirsty. And you say, okay, well, how thirsty are you? And could you drink a liter? And they're like, yes, I could. And so what is that going to be? What they are drinking, you're going to end up with that person having a 1 liter glass of sweet tea. Would that be your V1 or your V2? That perfect. Great job. Great job. So the V2, this half is your final. And M1 V1 is your starting. Okay, so your friend tells you that, oh, I can drink 1 liter. Great. What would you do with this? Well, what you'd be able to do is you'd be able to identify the V1, which is the how much of your sweet tea do you need to use to make their 1 liter sweet tea? Could everyone give me a Y if that makes sense, or a P if that doesn't make any sense? Okay, so all that we'd have to do, and before I do this calculation, do we need to stress about units? I mean, we were talking about units earlier, but now do we need to? We don't. But what we do need to know is what units our V1 is going to come back at. So we've got 3 times V1 is equal to 1.5. I went ahead and did 1.5 times 1 to get me that 1.5. I'm going to divide each side by 3. That V1 gives me 0.5. What are my units for this? It's V1, so it's a volume. 0.5 liters. Could everyone give me a Q in the chat if, okay, yeah, I follow that. I gotcha. Makes sense. I can do that. Okay, awesome. All right, I'm going to clear my drawings here because I'm going to go through this right here. What are our, how do we do a percent concentration? Well, a percent concentration is something that you'd see like at the grocery store. Um, and this is going to be, what is the volume? This is a V by V percent, and this is a mass by mass um, percentage. This is percent by volume or percent by mass. So all that you would do is you'd say, okay, how much of the solute, what volume of the solute is used to make the total volume of the solution? What mass of the solute is used to make the mass of the solution? So if I had something that was 17.4 grams NaCl and my total mass of my solution was 100 grams, well, 17.4 divided by 100, and then we multiply it by 100, this is going to be a 17.4% solution. Now, this is a sort of calculation that you can kind of do in the opposite direction as well. You have, let's say that you had a 0.35% solution. What mass is required to make 100 grams of solution? Well, the great thing is that we have all this set up as 0.35% is equal to 100 times mass over mass. Okay, so I divide each side by 100. And that's going to be 0.0035. That's going to be mass solute over the 100 grams of my solution. What if you have grams of solute and liters of solution? Great question. So in that case, what we're doing is basically your scaling gets a little bit kind of distorted almost. So a percentage solution is really based on 100 grams of that solution. Okay, so if we had, let's say you had 7.4 grams of solute, and we made, well, that what you're describing, a liter of a solution, well, 1 liter, we have to think about like the density of water kind of as our basis. So let's say that we had 1,000 milliliters, which I'm going to say 1 gram per mill. So I'm going to say 7.4 grams of solute over 1,000 grams of solvent. Does that make sense? Give me a Y or an N, or did my explanation get messed up? Okay. So we do the same thing. 7.4 divided by 1,000. Multiply it by 100 because we've got to make it a percentage, in which case we would end up with something that's, if I can do the math in my head, it would be 0.74%. So if you think like it all kind of comes back to density of water as our basis solution. So there we go. Now, if you were trying to be much more technical or precise or something like that, then you'd maybe change the density calculation. You'd be more precise with those numbers. But that's going to be kind of what you're looking for. Okay. So being able to do all those calculations is extremely valuable. Um, I would pay particular attention to the molarity calculations and those three different levels of difficulty and rigor and challenge to those. Make sure you can do all three different levels. Now, after that, we kind of got into a little bit more molecular. Like, what does the molecule look like? Or what do these molecules look like? In which case, we had intermolecular forces. So we had intermolecular forces and intramolecular forces. Our focus for this was all about intermolecular forces. So, what are the forces that hold two different molecules together? And we looked at those intermolecular forces. We had the dispersion forces, also known as London dispersion forces. Those are your weakest. Dipole-dipole, also known as your dipole-dipole forces. Those are your kind of mid-range. Then your hydrogen bonds, those are going to be the strongest of the intermolecular forces. I always kind of think about it as the dispersion forces, also known as London dispersion and also known as induced dipoles. These are your weakest of weakest. Every single type of or every single molecule has these sorts of interactions. Dipole-dipole, those are a little bit stronger. Only your polar molecules will have those. Now, are so basically if a molecule is asymmetric, it's going to have dipole-dipole forces. Hydrogen bonding, those are the strongest of the weakest interactions. Those are your strongest of the intermolecular forces. You're always going to look for an OH, NH, or FH. If you see those, you've got something that's capable of hydrogen bonding. Now, I remember, or one of the questions that I like to ask is this molecule has H bonding going on. In which case, I'll throw H2O. Okay. Yeah, done. But what I like to also do is I say CH4, um, NH3, then let's see, let's go with MgH2, just to kind of throw a curveball there. And let's go with hmm, hmm, no, um, SH2. So only polar molecules of OH, NH, FH. We've got CH4. All of these have hydrogen. In which case, this is a question where some folks are like, well, they all have hydrogen bonding. They don't. They all have hydrogen bonded, but they don't all have hydrogen bonding. A single CH4 molecule or two CH4 molecules, they're not going to participate in any hydrogen bonding. They will have exclusively dispersion forces. NH3, boom, there's your answer. Because that has one of our three things that we're looking for. MgH2. Oh, I've never seen that before. Well, ask yourself, does it have OH, NH, or FH? Nope. Off the table. I don't care if oh yeah, that's really funky. That's got some sort of wild thing going on. Yeah, it might, but it's not what we're interested in. SH2, ooh, or H2S. Ooh, that's interesting. Yeah, it might be, but does it have anything that we're looking for? No, it doesn't. So hold yourself to kind of like a high standard and say, all that I care about for hydrogen bonding is OH, NH, and FH. If it has one of those, boom, it's going to. Another question that I like to ask is whenever I'll present two different molecules. And these two molecules, these two, will H bond together. Okay, so then I'll say H2O and CH4. Then I'll say H2O and NaCl. Ooh, that's interesting. I'll say NH3 and ooh, CF4. And then I'll say H2O and NH3. Okay, given these answer options, hydrogen bonding. Well, H2O, that can hydrogen bond, but I'm asking, can it hydrogen bond with CH4? No, it cannot. So that's off the table. Option B, H2O and NaCl. Again, H2O can hydrogen bond, but not with NaCl. So that's off the table. Then we've got NH3 and CF4. Ooh, that's interesting. That's interesting because I've got N and H, so check. And there's fluorine, but oh man, there's a couple of reasons why CF4 doesn't work. One reason is if you drew this molecule, it looks like this. Fluorine going off from each side of that carbon. Is this molecule symmetric? S for symmetric or a N for not symmetric? Yeah, it's symmetric. So what does that mean in terms of its polarity? It's nonpolar. So that's one way in which this is wrong. Another way in which this is wrong is, does this molecule, does it have FH? No. So that's another way that it's wrong. And I'm not saying this to be like, and that's why you're wrong multiple ways. I don't want to sound like that, even though I know that that kind of sounded like that. Instead, I want you guys to be kind of processing this information, being like, oh, okay, like this is the sort of question that I would fall for it in like four different ways. I know that I fell for this one because I'd be like, ooh, fluorine, yeah, that's enticing. But does it have FH? No, it doesn't. Trust your gut on that and say, well, there's a fluorine there, but I need to have FH. This molecule does not have FH. So it's out for those different reasons. And then last but not least, there are questions that you'll see that are like, ooh, H2O and NH3. That looks like it's so right. That's got to be a trap. It's not a trap. That one's so right because it's right. So this is this particular answer option is one that students come to me all the time. And after I explain this problem, they say, "Oh, you know what? I knew that. I knew that. But I picked C. I guess." And I'm like, "I'm sorry. I'm sincere in saying like I'm sorry about that. That's frustrating." But then they use this term. They say, "I guess I was overthinking it." And you don't have to answer, but does anyone ever feel like, yeah, I knew the answer, but then I thought about it four more times. I think I overthought that one. If you feel comfortable, put a plus in the chat for, yes, I've done that in this class. So that is something that's very common. And what I would do is just try to stick to like, okay, what is the simplest explanation? And try to go with that. I know that easier said than done, but that's like for hydrogen bonding, I would just say OH, NH, FH. If I don't see those three things, I'm not talking about it. I'm done with it. It's not, no, not interested. And that I think is going to be very helpful. Or I think that's kind of a good, and full disclosure, I struggled for way, way, way too long with understanding hydrogen bonding. Because I remember in some of my classes as a graduate student and an undergraduate, I'd be like, oh yeah, yeah, hydrogen bonding, yeah, definitely, totally, totally, yes. And then I would be like, I didn't really understand it well. Because I would overcomplicate it. Okay, now these intermolecular forces that hold things together, they ultimately make things stronger. Um, so the stronger the intermolecular forces, you're going to see things like boiling point be higher, and you're going to see something turn into a solid. Okay, so the last few pieces of information, I need to upload the marked up slide decks for 11 and 1113. I'll do that in just a little while. States of matter, this is all about, and I'm going to show you a slide that will be particularly useful. Nope. This one right here. I want you to know these terms. I want you to know and use water as your example, but understand, what I would do is I would say, what are the three states of matter? Solid, liquid, and gas. Now, what do we refer to water as in these different states? Well, water, I'm just going to put W. As a solid, we refer to it as ice. As a liquid, we refer to it, well, we just kind of refer to it as water. And then as a gas, what do we refer to water as typically? You could say steam or water vapor. Are all three of these terms things that people feel comfortable knowing and recalling this? Give me a slash in the chat if, yeah, I got those. I'm good. Okay. Now, with that, I think we know what it's called whenever ice is converted to water. Melts or melting. Okay. Then when water goes to water vapor or steam, it's vaporization. Okay. Now, whenever we see something convert from water to ice or a liquid to a gas, that's freezing. And then from steam or water vapor or a gas to a liquid, that is condensation. So these are all things that I want you to try to like relate these terms to your own like lived and spoken experience. Now, these are terms that I want you to feel comfortable with, but what I want you to do is just kind of think about them. Let's go ahead and eliminate ice. We'll erase that, get rid of that. I want you to use these terms or apply these terms with respect to states. So solids going to a liquid or a liquid going to a gas. These are the terms that we use. Now, there's one last one that I want you to be familiar with, and that is, I'm going to use orange. A solid going directly to a gas. That is known as sublimation. Sorry, I need to erase that. Sublimation. Then a gas going directly to a solid. That is known as deposition. Okay, so those are six terms that I want you to be familiar with and comfortable with navigating. How does a solid go to a liquid? How does a liquid go to a gas and vice versa? How does a solid go to a gas and vice versa? Okay, if you want to get a screenshot of that, go ahead and get a screenshot of that. This slide is valuable because it does show us kind of at the molecular level, kind of what's going on. Well, when we talk about a solid, all of the kind of molecules that make up that solid, they're in close contact and they're kind of in constant contact. A liquid, well, they're in closer, they're a little bit farther away from one another, and there's some movement to it, but maybe not a whole lot. Then in a gas, oh man, those molecules are just popping all over the place. And they are constantly colliding, they're bumping into each other and everything like that. Okay, I'm going to clear all of this in 5, 3, 2, 1, 0, done. Okay, now this diagram right here, is kind of the same thing, but the difference is, or the biggest difference is that this is relating pressure and temperature. So the way that you should expect questions for this and is to understand where the solid, liquid, and gas are. Supercritical fluid, don't stress about that. The questions that you'll see on your exam related to this are ones that I'll draw, and I'll say, okay, well, here we go. And I'll give you a pointer like, okay, you are pressure goes up, temperature is going up from left to right. So there's our origin. And I'll say you are at position A and the temperature increases. What will this substance do? Temperature A and the temperature, or sorry, substance, a sample in at position A, at point A there. If the temperature increases, what will be observed? Well, it will go from a solid to a gas. Okay, that's sublimation. Okay, then I'll say A goes to B, B goes to C, C goes to D, D goes to E, and E goes to F. And I'll give you questions that are like, when you're transitioning from E to F, what are you doing? You're going from a liquid to a solid, so that is freezing. Give me a Y or an N in the chat if you follow that. Okay. Now, probably the most complicated I would make this would be something like, okay, A goes to B, to C, to D. What are you witnessing? Well, A to B is sublimation. Kind of, my question would be like, what's the sequence of events? We got sublimation, and then we're going from a gas to a liquid. That would be condensation. Then a liquid back to a gas from C to D. So this is A to B, then B to C, then C to D. C to D, liquid to a gas would be vaporization. And my question would basically be like, what is taking place? And I would have those terms and I'd shuffle them around. Those would be your answer options. Okay. I'm going to clear all the drawings here. So that's all our different states. Ionic substances versus molecular substances. One of the things that I want to stress about ionic substances and use an example. I always think about NaCl, table salt. If you got table salt and you put it, you got a bunch of table salt, those are crystals. Those, yeah, they're salt crystals. Um, could those salt crystals melt? Yes, if you get the temperature hot enough. So they will have a very high melting point. Okay. If they have a high melting point, they're going to have an even higher boiling point. If you had table salt, think about, has anyone ever, like maybe, I remember I did this when I was in undergrad. I was going to make pasta. And so I got some water and I put some salt in it. And then my ADHD took over and was like, "Hey, Joel, think about anything but the thing that you were doing." And I was like, "Done." Um, I left that salt water on the range oven. What happened to that salt water? Well, I saw some state changes. The liquid converted to a gas. Okay. And I had a lot of salt in there. What do you think happened to that salt? Well, it stayed in the pan. And after that stayed in that pan, what do you think would happen? Well, the salt that had crystallized, is that salt going to get hotter and hotter and hotter as it stays on the pan, on the burner? Yeah. Eventually, if the burner in my kitchen was hot enough, if it got to like, 1500 degrees Fahrenheit, that salt would go from a solid to a liquid. Um, would I want to, if I poured that liquid salt on my arm, what would happen? The burn would be so extreme and so intense. Compare that to, well, if NaCl as an aqueous AQ substance versus NaCl as a liquid. Liquid NaCl versus aqueous NaCl. This right here is when it dissolves. Could I pour salt water on my arm? Yeah, no problem. Liquid NaCl. I do not want to pour that on my arm. Does everyone understand the differences between AQ and L? Add a 9 to the chat if you do. And if you don't, then add any other character and add a, follow-up question. Okay. Okay, great. Um, so now I'm going to clear all this and close that. We talked about gases, and actually I'm going to go to last Thursday. Because with gases, we talked about the ideal gas law, and we looked at our different relationships between pressure and volume. Um, so if we're changing one variable here, if pressure goes up, what happens to volume? Pressure goes up, then volume goes down. If you're only playing around with volume and temperature, if temperature goes up, volume goes up. If temperature goes up, what happens to pressure? Pressure goes up. If volume goes up, or sorry, if number of moles goes up, volume has to go up. So remember keeping it as these three are dividing. This is multiplying. The multi is indirect. This is an indirect relationship. Dividing is a direct relationship. Now, if you change more than one variable, or if you change, more than one variable, then you have to, or if you talk about or know about more than one variable, you have the either combined gas law or the ideal gas law. And then last but not least, we talked about acids and bases. Like I said, I'm going to upload the modified slide decks for these. When we talked about acids and bases, we had the Arrhenius equation, or sorry, the Arrhenius example of an acid and base, and we also had the Bronsted-Lowry. And so the question was, is something giving up a proton or is it gaining a proton? If something gains a proton, then it is a base. If something gives up a proton, then it is an acid. Okay, I'm just going to go ahead and stop there and ask, does anyone have any questions? And if nobody has any questions, I hope you guys have a great day. That's all that I've got for today. If you have questions, you're welcome to hang around. I'm going to keep recording. And so if you have questions, feel free to ask them, and I'm going to open up a blank PowerPoint slide so I have a blank place to work. So have at it, folks. Thank you. I was trying to do some of the practice questions, but having trouble. Okay. Question 32. Let me get that one real quick. Okay. So question 32 reads, okay, I'm happy that you asked about this. This is about strong and weak acids, and we actually did not get to strong and weak acids. So we're going to tackle that after the break on Tuesday's lecture. So question 32, I'll go through this exam and send out a message about which ones to kind of uh, not prioritize or ignore because we haven't covered it. But the answer to this one is HCl, just if you're curious. And were there any other ones on this practice exam that were like, huh, where'd this come from? Okay, cool. So I've got this. Okay, so I mean, let's see. 40 sample of gas occupies 30 liters. Doable. Solid changes to liquid, melting, constant temperature, volume increases, pressure is going to increase. 36 is B, it's a base. 35 is A. Blue litmus paper turns red. It must be acidic. Has the highest hydrogen ion concentration. That's going to be pH 2, so A. 18. Okay. So 18 reads a 500 milliliter sample of a gas at 27 degrees is heated to 127 degrees Celsius. What is the new volume? Okay. So for this one, let me make sure. Okay, so this is P1, V1. No, no. So, sure. So this would be looking at. So this is relating temperature and volume. So that's going to be the T1 over V or T1 V1. So this would be on Thursday the 6th. And the equation is temperature and volume. So that would be the Charles's law. Charles's law, so it is V1 over T1 equals V2 over T2. And maybe the biggest part of this one is to make sure that you are converting the temperatures from degrees Celsius to Kelvin. So this, yeah, V1 over T1 equals V2 over T2. Okay. Well, I'll go ahead and stop the recording there unless anyone has anything else. And I will see you guys maybe in office hours today or tomorrow. Just let me know, and I'll talk to you later. Thanks for coming, everybody. Thanks for your participation. I really appreciate it.